Hello, welcome everybody to another discussion on IQ question set 5 for MATH155 SFU summer 2020. This IQ, we're talking about integration techniques and a little bit of applications of integrals. So the first part of the very first question is first of all asking you to compute area between the curves, and then after that you're supposed to know volume of revolutions to find the volume. After that, followed up with the question number 2, we're going to talk about abstract techniques that are fundamentally the building blocks for what you're going to learn in the future for integration. So we're going to talk about that in a bit. So without further ado, let's get started. The first question here is based upon properties of an ellipsoid. And if you guys don't know what an ellipsoid is, it's just an ellipse. It's a 3D shape that looks like an egg, okay? And then that's called an ellipsoid. However, we're going to start to talk about this problem in pieces. If you see an ellipsoid in 2 dimensions, you're supposed to see an ellipse. Okay, so here they're talking about a region bounded by this curve. Okay, this curve is just a positive square root function. Okay, many of you guys can just plot it using transformations of regular functions. Like you can definitely use a transformation. This is the square root of x. Then this is the square root of minus x, and then so on and so on. And you can kind of come up with the graph of it. But just generally speaking, for the equation of an ellipse, there's a very specific method that we usually follow. Okay, so we're looking at the region bounded by this curve and the x-axis. So make sure you watch that out. We have to sketch the region, make sure to label the boundaries and intersection points clearly. So let's try to see. If you have an ellipse like this, where the x-intercept is a, minus a, that's b, minus b. So basically the points that you're looking at are just going to be a comma 0 here, and then so on and so on. So you got to watch out whether when you're trying to draw an ellipse equation like that, that's the key step. Now, in this case, all we have to do is either we can convert it into the actual form, like in this general form. That's how it looks like. The equation is going to be x squared by a squared plus y squared by b squared equals to 1. That's for an ellipse that has an x-intercept of a minus a and a y-intercept of b minus b, right? So that's it. Now, if you try to isolate this equation and rewrite it algebraically, so first of all, what you'll do is you'll square both the sides. You get 1 plus x squared divided by 9. Then you move this x squared divided by 9 on that side, so you're going to get, oh my god, that should be y squared equals to 1 minus x squared by 9. And you move this over to that side, you get x squared plus 9 plus y squared equals to 1. And that's what you have here. And I just wrote the 9 at the bottom is 3 squared, and I wrote a 1 squared at the bottom just so I can easily identify what a squared and b squared are, and then hence a and b. So if you can figure that out, then if you draw the sketch, you know the x-intercept is going to be 3 and the y-intercept is going to be 1. So when you draw that, because this is a positive square root function, so the half of an ellipse is going to be the half that's on the top. Okay, that's why you draw the ellipse like this, just a half portion of it. These points are minus 3 and 0. That point is 3 comma 0 because of the intercept being 3 here. And the top bound, it's going to be 0 comma 1 because the top intercept is just 1. And you got to make sure you draw this boundary as well. You got to make sure you draw the x-axis in the blue as well, because this bounded region is what we're looking at. Kind of looks like a potato wedge. And that's pretty much it for the first part. Now what they want you to do is set up an integral to find the area of the region. And then, so first of all, we got to set it up, and then we got to evaluate it using a trigonometric substitution. Okay, so they're very specific here. They're specifying a method and a specific approach you should take in that method. And I just want to take a step back and kind of talk about this for a second. So generally speaking, in your course, you will have 3 major techniques when it comes to solving integrals. Okay, 3 major techniques. The very first one is the substitution. You might have already learned about it, and a special branch of that is called trigonometric substitution. So that's the very first one. Then the second technique that you will not talk about in this particular IQ is by parts. So integration by parts is also a method that you probably already know about now. And the last but not the least is by partial fraction decomposition. Many of you guys are still learning about it because it's pretty recent in your notes and stuff. So I would say if you're not too good at these, it's okay. You can still take time to learn about these things and what's happening. I already posted up a video. You can find that playlist on my channel about integration techniques. I talk in detail about trig substitution and partial fractions because those are the ones people usually have trouble with. By parts is very straightforward sometimes. So you can go over and look over that. That's one of those things. But again, these are just the major things that you'll be learning. Now in this particular question, in part B, we're trying to use this method here. We're trying to use trig substitution. So if you don't know how this method works or what I should do and why am I doing certain things, I will not be answering those questions in this tutorial because I more want to discuss the question rather than the method itself. So if you need help with that, definitely you can reach out to me anytime, or you can watch the videos on my channel about this trig substitution and everything should make sense. Okay, so let's get started with the question here. First of all, we got to find an area, an integral that represents this area. Okay, so you know if you take an integral of f of x, some function, from some a to b, this is equivalent of taking the area under the graph of f of x from a to b. Okay, that's the basic idea, right? So knowing that if you want to take this area, all you need is to take the integral of this function, which is the function that is given to you as square root of 1 minus x squared divided by 9, and the bounds on that should be from -3 all the way up to 3. Okay, so that is why you have this integral set up here to compute the area, and that was just pretty much the first part of it. Set up the integral to find the region area. That's it. Now we got to start to write the process. We got to evaluate this. So because this is a definite integral, we should expect it to be a number, a singular number that we can easily find using the method, and the number represents the area of this bounded region. Okay, so let's get started. Now the first step that I usually like to do here is to rewrite the expression to make it very obvious for substitution. Okay, the only thing I did here is because I had an x squared divided by 9, I just wrote it as x over 3 whole squared, and there's no harm in saying that. Okay, so I rewrite it like that. The bounds are still going to be -3 and 3 and all of this thing. So now is the point where we actually carry substitution. Okay, when we do the substitution itself, what I'm substituting here is because of the method. Okay, there's a reason why I chose it to be this way, and the reasons are going to be answered in my videos where I talk about what the method is and how we actually solve it. Right now here what I did is I substituted x plus 3 as sine t, okay, where t is another new variable that I introduced. Right now my integral is in terms of x. Okay, now because I'm substituting it in terms of t, I got to change everything in terms of t. Okay, so first of all I changed this piece in terms of t. I still have to change the bounds, and I still have to change the dx. Okay, because I got to put the dt as a differential element for it to be able to integrate. Okay, so that's the first lead intuition towards making it easy. So that's it. All of the other things are going to be born out of this. So we got this expression. Now from this I want to find dx. So all I do is, if you are weak at that, please try to brush it up, but all you got to do here is do implicit differentiation. Okay, you want to do implicit differentiation of this function here with respect to x. So the derivative of x over 3 with respect to x is 1/3, and derivative of sine of t with respect to x is going to be cos t times the derivative of t with respect to x, dt by dx. So we got this expression. In this I have a dx and I have a dt. So I want to isolate what dx is in terms of dt and of course t. So all you got to do is you send this over to that side and you bring the 3 on this side. You get an expression that dx is just equals to 3 times cos t times the dt. Okay, so we got the dx element taken care of. We got taken care of this. All we got to do is talk about the bounds now. Okay, so we got to look for the bounds, and then we got to follow the same relationship here. Because of this expression, you can isolate for t here. When you isolate for t, all you got to do is take sine inverse or arc sine of both sides. When you do that, you get t equals to sine inverse of x over 3. Okay, so now we have an expression relating t with x in which we have isolated t separately. So now to figure out the upper bound, all you got to do is take the upper bound on x and plug it in this expression. Okay, whatever the upper bound x was, you plug it in, and then you get this expression. So t upper, which I usually use to kind of like signify what I'm trying to calculate, is sine inverse of x upper divided by 3 because of this relationship here. And then we get sine inverse of 3 by 3 because that's on top. And then we get sine inverse of 1. So you're pretty much asking yourself, what angle gives me a 1 for a sine value? And that happens to be pi over 2. So we figured it out, that's pi over 2. So now we have a new bound on t upper, that's pi over 2. And it makes sense. Why is t upper an angle? Because t is going inside a trigonometric expression. So it must be an angle. Okay. Now similarly, we got to compute the t low. And then to find the low, you just take the lower bound and you plug it in the same expression. Because that expression governs everything, right? We got that thing, and then we know t low is just sine inverse of x low divided by 3. And then you do sine inverse of minus 3, of course, in this case, divided by 3. So you have a sine inverse of minus 1. So you're just asking yourself what angle, when I plug it into a sine, gives me a minus 1. And that happens at 2 angles. So either you can go to the other way. You can go 3 pi over 2. That's also a possibility. Okay. But to just keep it simple, we can just do negative pi over 2. Okay. So that's just for simplicity. You could have definitely chosen the other one. You would still get the same answer, so no trouble at all. Here I choose minus pi by 2. Okay, so we've got everything delta. So now this integral is going to transition into something that is something that we were familiar with, and it's easy to solve, but it happens to be in the t variable world. And now we have everything in terms of t. We got the bounds in terms of t, we got the dx in terms of t, we got this side in terms of t. So now it's the time to compile the whole integral and see how it looks after substitution. Okay, so we're going to go piece by piece. So first of all, the bounds here are minus pi over 2 to pi over 2. That's the new bounds. Now inside, you had x plus 3, which was turned for sine, right? So now you'll be having a square root of 1 minus sine squared t. And that's what you have here because of the square root square outside. That's this. And now 3 cos t dt is the substitution for dx. Because we figured out that dx is just equals to that. So we plug it in there. So we have a nice an expression that we can solve with. So cool. So now we gotta use some algebra and some trigonometric identities to make it look easier. And that's the whole purpose behind trigonometric substitution method. Because when you change these things from algebraic expressions to trig expressions, you can use the identities to solve them up very easy. Okay. So now this is a 3 that's being multiplied. I pulled this outside because you can pull out the constants from the integrals. This, however, 1 minus sine squared t, because of the world famous identity, could be written as cos squared of t, because sine squared of t plus cos squared of t must be equals to 1. So if you isolate 4 cos of t, you're going to get that. So we got that part. And times this guy is going to still be hanging out there. Okay. Now, a square root of cos squared t will just give you a cos. And you have another cos outside. So all in all, you'll end up with a cos squared t inside. Okay. Because square root of cos squared will give you a cos, and the cos outside will become multiply with it, eventually giving you a cos squared t. So we got this. This is the integral. And it looks pretty nice, to be very honest. Okay, it doesn't look that haunting like this guy here. So what do we do now? Now in this case, we can just either jump up with a straight up question identity that we kind of know of. But there is no function that you can find whose derivative is cos squared t. Like, not out of your head, okay? And it'll take some time for you to do that. So we don't have a direct antiderivative in our head, because usually if I give you this guy, cos t dt, the direct antiderivative of this is going to be sine t plus c, because you know when you take the derivative of sine, you get a cos. Okay, that's something that you can figure it out. So that's a very simple standard integral, but not so much with the cos squared of t. Okay, so we have a trick that we usually use to kind of work with all these ones. So this trick is called the half angle, or sometimes people call the double angle. The double angle formula or half angle formula. What it does is it gives you an expression where cos of t, okay, cos squared of t, could be written as another function of cos without the squares. Okay, so that's what we can do here. In this case, we got 1 plus cos of 2t divided by 2. That's the formula. And this is something you got to remember from memory. Okay, you get good at that the more you practice. So we got this expression. We can substitute cos squared with 1 plus cos of twice of that angle divided by 2. Okay, so remember, this is cos of twice of t. Okay, so don't mess it up. It's not cos of 2 times t. Don't get confused with that. So that's this divided by 2. So now if we substitute that in this case, we got that expression. Now what you got to do is you got to take the antiderivative of this. So now that part is something that I want to leave out to you. This is do it yourself. I want to make sure everybody understands this thing, so I got to put some nuggets here where you have to do the work yourself. I will walk you through it. What you can do is you can separate these two. You can write this as 1/2 plus cos of 2t divided by 2 and the whole integral. And then you can take the integral 1/2, which you can figure it out very easily. And you can take the integral of cos of 2t divided by 2 using the method of u substitution. You guys know how to do that, okay? But I just skipped through that because that's not the purpose of the video. I want you guys to be able to, learn these things all yourself. So that's that. The antiderivative of this function is right here. Yeah, you can verify your work and you can check it out. If you have any questions, you can definitely reach out to me. So we got this. And now all we got to do is we got to evaluate it from the bounds of minus pi over 2 to pi over 2. So we got that expression. And all the last part of the work is just to plug these numbers in and evaluate it. So to do that, you plug in the pi first. You get 3 times pi over 2 divided by 2, which gives you 3 pi over 4. And then you plug in here. In this case, we have 3 sine of 2 times pi over 2 divided by 4. So we get that pi just left here. And then same thing with the negative pi over 2, you get that. With the negative pi over 2 there, you get this thing. And now another thing that you can remember is sine of pi and sine of minus pi are just going to be 0. So these two guys go to 0. So you're only left with this expression 3 pi over 4, which is from this guy. And then minus of 3 pi over 4, which gives you a plus 3 pi over 4. And the total answer is 3 pi over 2. And that's pretty much how you solve the question. Okay. And we expected it to be a number. You can definitely work out your way to solve for the area. You can confirm this answer and it makes sense. Okay. That's just the way you solve this problem. Easy peasy. Now the next thing is what they're asking you to do is suppose the region is revolved around the x-axis to form a solid of revolution. We call that ellipsoid. Okay. So you can imagine in your head, if you rotate this thing, if you rotate that cross section and make a 3D object from it, then you're going to get an ellipsoid. And then we got to set up an integral to find the volume of the solid and then evaluate this integral using integration technique. And you do not want to give a geometric expression. Okay, so we're going to do this like that. That's the region. We're revolving around this axis. And then the thing here is to decipher what method you want to use. If you guys have learned multiple methods, that's fine too. If you haven't learned multiple methods, then this method will kind of make sense. So how we do that here is we take a very small cross section. A very small cross section, which is having a thickness of dx because it's on the x-axis. And this height here is just the function's value, right? So that's pretty much it. What we want to model this is going to be modeling as a disk. So if you rotate this cross section around here, okay, then you're gonna end up with a disk. Okay, of course you can't see it right now when you rotate it like this, but if you were to look at sideways, you're gonna have a disk with some thickness here. Okay, which we're gonna have a center point like this. This is the measurement of the radius. This is another radius, and if you look at it from this way, you'll see a disk with a radius r. So pretty much what you're trying to do is, if you think about a reverse process of this, to kind of give you more intuition in this, is if you have an ellipsoid already, a 3D shape, and you cut it down in different sections, okay, and you're gonna have infinite amount of small cross-sectional discs that you cut out of this, and you lay them out flat, you'll see you have smaller discs, and it gets bigger and a bigger and a bigger, and then smaller and a smaller and a smaller. So these are all the discs that you have lie down over there in front of you, like you flipped out. So it's pretty much if you take a solid and you slash it up into like very small thickness, infinitely many discs, and then you have it laid out like this, the total volume of the solid is equals to the sum of the volume of all of these discs. And that's why you have an integral there. Okay. What we want to do is we want to figure out an integral that represents the volume, the area or the volume of one of the discs, and then you want to add them up over the whole interval. So that's why we use the disk method. And in this case, if you have a disk, the volume of the disk that has a thickness of dx will just be area times the thickness. And the area of such disk is just going to be pi r squared times dx. So Using that idea, all you got to do is represent the radius as a function of that's varying. Okay, in this case, we're going to write the radius as a function of x, and that's what I did here. So the radius here, in this case, I just have an outer because usually we use washer method. So if you have a solid that is hollow from the inside, let's say you have a bullet shell, right, like this, that's hollow from the inside. In this case, when you slash it out, you're going to end up with washers, or like, you know, donuts that have some gap in the middle. So in this case, you have an outer radius and an inner radius and those ones. But in this case, you just have one single solid. You don't have a hollow portion in there. So the inside radius is automatically 0 for these kind of things. And if you are not too sure about this method, please talk to me about it, or, you know, watch some tutorials about this. If you need help, I can recommend you do a lot of good tutorials out there that show you a graphical way of imagining this. And I know this topic is usually thrown in the bus when you have a midterm or right around the corner. Nobody focuses too much on this, but I hope you guys know this. So I'm not talking too much in detail about this one. So that's it. We got an inside radius and the outside radius, and the expression for the volume is the integral. So summing up all the disks from -3 to 3, and you're having the volume of each one of them. And each one of the volume is pi r squared times dx, where the r outside is a function of x, because the radius varies as you move, right? When you start at -3, the radius is very tiny, and then it becomes very big in the middle, and then it starts to shrink down back all the way to 0. So that's this. And now r out is this function here, so you got to square that, you get this expression, and then you see an integral that you can take it easily, take the antiderivative off. So when you expand the inside, you're going to left with pi minus pi over 9 times x squared, and then antiderivative of this guy, or the integral, is just going to be pi x for this, and then pi over 27 x cubed for that one. You can definitely check it yourself. So that's also a d of I. And now the last step is to evaluate it from -3 to 3. So you plug in the -3 in the top 3. So this is what you get here, it's an expression. Do some little algebra, you get 4 pi as the answer. Okay, you can verify all of this, and if you need more clarity on that, just reach out to me. Okay, you know how to get to me. And that's pretty much it for the first question. Now we're going to talk about abstract integration, and they have a giant warning in front of you. These integrals are going to be tough. You'll be dealing with arbitrary functions, and they suggest you to try, you know, get comfortable with less abstract functions where you have actual functions instead of the placeholder fx and gx, and they could be differentiated and all those stuff. So make sure you do that, but it's okay to not do that. It's completely fine. Now in this case, the first integral we're talking about is IA, and that's integrating g double prime of f of x. So that's a compositional function in which you have an f of x function that's plugged inside the input of g of double prime of x. So make sure you remember that. This is it, and then you have a times f prime of x times dx. So this here is the very fundamental way of approaching the questions that could be solved using substitution. And the reason why you do that is when you substitute this to be something simpler, then you can take the integral very easily. Let's say instead of having g of f of x, you just had double prime of x. Let's say, okay, if you have that, then the integral of double prime is just a single prime, right? And the integral is double derivative, or the antiderivative of the double derivative is just the one single derivative. So you could have dumped that very easily. So what the aim here is to make this guy look very easy. So how you do that is you go with the intuition and you substitute it. And then to help out the substitution, you must have its derivative outside there being multiplied with dx. That's a must. If you have that, then you can easily make sure the substitution method works. And I'll show you. So we took the f of x and you substituted it as u. Now, because you're changing the variables in terms of u, you got to make sure you get rid of everything else that's in terms of x. So that's already taken care of. We got to take care of the dx. So we derive this expression to find the relationship between du and dx. This guy, derivative with respect to x, will give you du by dx. This guy's derivative with respect to x will give you f prime of x, or f single derivative, right? Now, you can isolate for dx from here to be du over f prime of x. And when you plug in all these things inside the integral, you see the magic happening. When you plug it in, this guy becomes g prime, double prime of u. And then you have this f prime of x hanging out there still. But when you substitute for dx, that du divided by f prime of x cancels this f prime of x. So now you have a very simple integral. And that's the whole idea of substitution. When you have that very basic integral, you can definitely just take the antiderivative of g double prime of u du, which is just going to be single prime, so g single prime of u plus c. That's that, okay? And then all you got to do is, once you're done with the substitution, because the question did not start with u, it started off in terms of x, so your final answer should be also in terms of x. So all you got to do is whatever you chose as u, you got to plug it back in. Okay, so I chose the u to be f of x. I plug it in there, so the final answer is g prime of f of x plus c. And that's how you do the first one. It just kind of looks daunting because it has a lot of weird things happening here. But if you have a bigger idea of what the trigonometric substitution is about, or like the general substitution, how it works, it should be pretty okay to understand what's going on here. Okay, that's this. Now in IB, all we got to do is we got to repeat the same thing. Same thing. Now, instead of having a function and its derivative as placeholders there, you have actual functions. In this case, you have a f prime, which has a sine of x plugged in. And you think to yourself, okay, if this was just f prime of x, then this integral would have just been f of x, right? Very easy. But because it has a sine x, you just can't do it yet. But then you have this thing in your head, you see that the substitution could work because you have a sine x and you have its derivative outside being multiplied with dx. So you can definitely make the substitution work out. So that's easy. Now we'll start to carry out a substitution. Now, just like how we did in the previous example, in the very first one, the first question, we're going to keep on changing everything in terms of u, the new variable that we're going to introduce. You got to mind that this integral on the top and bottom had no bounds. So this is an indefinite integral. Okay, this is not supposed to give you a number, it's supposed to give you a function. Okay, but on the other hand, this one is a definite integral, so you're expecting a number of value, not a function. Okay, so you won't have a f of x, you will have some values, and let's see what those are. So you go ahead and you substitute u equals to sine x, and then when you take the derivative, you get cos x dx equals to du. So you're trying to say this bubble here, cos x dx, is just going to be equals to du. Or you can do the other way too. You can find dx and then substitute, you'll see it pop away. Okay, no difference at all. So we got that thing, and then we got to figure out top bound. So because the relationship is right here, you got to take the top bound, you got to plug it into this relationship. So the top bound is u equals to sine of pi, which is 0. And then the lower bound is plugging this guy inside this place. You plug in sine of pi over 2, you get u equals to 1. So that's it. So now the new integral after substitution will all in all become like this. So first of all, we got rid of the sine x to be u. So that's that. And then the du over cos x is what you get here because of isolating dx from here. This cos x and that cos x will go away. You have 1 and 0 at the bottom bound and top bound respectively. Okay, that came out from these guys. And that's it. It might look weird because it's the inverted way, but don't worry about it. It's just how it turned out. So now we have a very simple integral. An integral from 1 to 0 of f prime of u du. And because the antiderivative of a derivative is just the function itself, so this answer is just going to be the function f of u evaluated from the bound 0 to 1. That's it. And now to find the thing, all you got to do is plug in the top bound minus plug in the bottom bound. Okay, so function plug in the top bound minus function plug in the bottom bound. These are some values of the f of x and g of x function, which you don't know of, but these are going to be values. These are not functions. Okay, so all in all, if you knew that f of x is a function that they give it out to you and you evaluate it using a number, you plug it in, then you're gonna be able to find those values very easily. Okay, right now we don't know them, so we're gonna don't touch that. That's it. So this is just how you do this part here. Now the last one is kind of tricky. Okay, it makes use of the new method that you might have learned just before this video got posted, or just like the week before, and that method is integration by partial fractions. Okay, and the reason why we do that and why this method exists and what's going on and blah blah blah, it's all answered in my videos that I already made about this method. So I'm not going to go in details about those. I would rather, try to just solve the question itself using the method. Okay, so here what you're going to do here is we have gx squared 5g of x plus 8 g of x minus 2 whole squared times g prime of x. So right now, right off the bat, you see that you have a function and you have its derivative being multiplied there. So substitution is the way to go, okay, because that will help you simplify this thing. So all you do is you take this g of x, okay, and you substitute it as u. So what you have is, when you take the derivative of this side, you get g prime of x, and the derivative of the other side is du by dx. When you see that, you isolate this expression. So all of this bubble here, or whatever's in that thing, just becomes du. And this expression could be simplified to just that thing. Okay, where g of x is now replaced by u's. So you have a u squared on top because you have g at squared, minus 5u plus 8 now. At the bottom you have a u times u minus 2 whole squared times du. These kind of expressions require integration by partial fractions. And how you know that is because the degree of the denominator is bigger than the numerator. Okay, and that's just kind of hinting towards what you got to do is partial fraction. So partial fraction decomposition is nothing special. It's not even an integration technique. Okay, partial fraction decomposition is just a method to break down this expression into individual factors at the bottom. Okay, right now I have a u minus 2 whole squared at the bottom combined. I wanted to be able to write this thing as an expanded fraction in which this fraction is nothing but equal to sum of these three individual fractions. And the rules of how you determine how to expand, what expansion to choose, what kind of form you're looking at, all of that thing, all of those questions are answered in my video. Okay, so I would definitely recommend you watching that before you want to solve it yourself or you want to try it out. So in order for that to match up, in order for this thing to be equals to expanded form with some ABC arbitrary constants, I need to make sure that their numerators after when you take the least common multiple are the same. Okay, so if you do that, you equate the numerator with the least common taken numerator on the right side. Okay, there's a way to do that, and you guys can check it out. So don't get confused on why I did this. If you have your own way of doing the partial fraction method, it's completely going to be fine as long as we get the same a, b, and c. Okay, so let's walk through it. We got this expression. So this equation must hold for all a, b, c. Now all I got to do is I got to find some unique values so that I can identify what those a, b, c's are. Okay, so I know if I plug in u equals to 0, because of having a u here and a u here, these factors will go away. And I'll only have an a, which I can isolate for that. So when you plug in 0 into that expression, you just get 8 on the left side. On the right side, you just have a times 0 minus 2 whole squared, which is going to give you 4a. Okay, from that expression, and then these guys are going to be 0, so you get that a equals to 2. Good. Now the other way we can find out is c. Because if you choose u equals to 2, then this factor will go to 0, and so will this guy. Okay, so they will go to 0, you'll only be left with c. So when you plug in u equals to 2 in this side of the equation, you get 4 minus 20 plus 8. And then you get an expression from there as 2 here on this left side, and then you have a c only left here because all of these guys are going to be 0, and it happens to be 1. So we have a, we have c. Now we could just use manually any point that we want to use to find the b value. Okay, so we plug in u equals to 1 just out of curiosity because 0 and 2 are already taken, so I just plug in 1. So we'll plug in u equals to 1 and plug in a and the c values that I know. So on the left side we have 1 minus 5 plus 8, which is 4. On the right side you're going to have the a value 2 times 1 minus 2 whole squared, which is 1. So we got just 2 on that side. B is going to have a minus 1 because when you plug in u equals to 1, you're going to get minus 1 there. And then plus c is because c is 1, right? And then you plug in u equals to 1, you're going to get 1 there. From there you isolate, you get b equals to minus 1. So this method could be different for you as well. There's multiple ways the prof teaches it. Okay, so there could be comparing coefficients. There could be a lot of ways. I talk in detail about how I perform these methods in my video, and then you can look over those to learn it, or you can follow your own way too. So there's no trouble at all. So I figured out a, b, and c, a, c, and b, and now we have all of these. We can write this expression in the expanded form with those constants a, b, c. So you plug in a as 2, so you get 2 over u, and then you get minus b u minus 2, and you have 1 divided by u minus 1 minus 2 whole squared. So we got the expansion. Now the idea here is if you were taking the integral of that, then it will just be equals to taking the integral of this side, right, with all those constants and stuff. So that integral is just simply the integral of this guy now, which you have to do it yourself. So this is DIY, okay, because these are standard integrals. Integral of 2 over u is 2 ln of u. It's not too hard to remember that. And then integral of minus 1 over u minus 2 is minus ln of u minus 2. Absolute values, of course, because ln is only defined for positive values. So you don't know what domain you're working with because you don't have any bounds here. So to be safe, you put the absolute value out there. And you have a plus 1 over u minus 2 whole squared. Its antiderivative, or the integral, is minus 1 over u minus 2. That's it. And a plus c, of course. Now, this answer is pretty much done. You have the integral in front of you. The only thing that you need now is to plug in the function in terms of x, because you started with the terms of x. You started with g of x. You didn't have a u there. So u was just there to help you facilitate this thing into something easier that you can work with. And now you got to come back and plug it in terms of x. So you take u and you substitute with g of x. So the final answer here will just be 2 times ln of g of x, because g of x goes there, minus ln of u minus 2 is g of x minus 2, minus u minus 2, 1 over u minus 2 is just 1 over g of x minus 2, plus c, of course. And that's how you solve the very last one. So that was it. A very quick tutorial on this IQ. And if you guys have any questions, you know how to reach out to me. And thanks for watching.